So now let's look at our cations. So like we said, cations can act as acids, but they need to somehow produce a hydrogen ion, whether from water or from the cation itself. So we already looked at ammonium. So ammonium is the conjugate acid of ammonia. So if we were to write out the reaction for this one, excuse me, my pen's not on. So we have ammonium in water, and it would give up a hydrogen to make ammonia, leaving behind that hydronium ion, which is the same as the hydrogen ion. We could also have something like this. This is one of those amino groups we mentioned. And yet again, same thing. It could react with water and give up a hydrogen to produce, sorry, yet again, that hydronium ion. So all of those behave the same overall. Now looking at our salts, where we said our cations can behave as such. Here we have sodium. Now, sodium cannot release a hydrogen, but whenever it reacts with water, it can make water release that hydrogen. So if water releases the hydrogen, it creates an H plus, and leaving behind a hydroxide that pairs up with the sodium. Now, this is one of our strong bases, meaning that it will turn back into the ions. So anytime it's going to produce a strong base, this ion is going to end up being neutral, because instead of producing that base, it's going to turn back into that ion overall. All right, so the process where we are trying to determine if a salt is going to be acidic, basic, or neutral is we're going to go through salt hydrolysis. So remember, a salt is any ionic compound that is not an acid or a base. So it is not going to start with hydrogen or end in hydroxide. That includes like our weak base of like ammonia as well. So our cation is not hydrogen and our anion is not hydroxide. And whenever a salt goes through hydrolysis, remember hydro refers to water. So we are going to react it with water, and lysis means to break apart. So we're going to put the salt in water to separate the salt and break it apart into ions. So each ion will end up reacting with the water. Now, when looking at salt hydrolysis to determine if this is acidic or basic, you have to look at both ions to determine the nature of the salt. It's possible that the cation is acidic and the base is neutral, or the anion is neutral. It's possible that the cation is neutral and the base or the anion is basic. It's possible that they are both neutral. It is also possible that one is acting as acidic and one is acting as basic. So you have to kind of look at both of those to determine it. So we're looking to see, can the cation act acidic? So can the cation produce those hydrogen ions or hydronium ions? And we're looking to see if the anion can act basic and produce those hydroxide ions. So here's what it looks like. So we're going to look at potassium acetate. We do need to split this into the cation and the anion. So our cation and anion split is we have potassium ion and the acetate ion. So we need to react both with water to see what they are going to produce. So if I react potassium with water, and then I'm going to react the acetate with water. So potassium and water, potassium, remember, should be acidic and give up a hydrogen. Potassium can't give up a hydrogen, but it can force water to give up that hydrogen by taking on that hydroxide. Now, potassium hydroxide is a strong base, meaning that this will turn back into ions. So this cation is neutral because it would try to produce a strong base. Whereas if we look at the acetate ion with water, acetate, remember the hydrogens inside the acetate cannot be given up, but it forces water to, it accepts that hydrogen because it's negatively charged to H3O2, which will leave behind hydroxide floating around. This acetic acid is a weak acid, which means it will not necessarily split back up. Some of it may split back up, but a lot of it will stay together. This produces hydroxide, meaning that this is acting as a base. So since only our anion acts as a base and our cation is neutral, this overall is a basic salt, because overall that base is produced. All right, let's look at a couple more examples. Here we have sodium cyanide. Yeah, again, we're going to split it between the cation and anion, and we are going to react both with water to see if this salt is acidic, basic, or neutral. All right, so looking at our cations, so sodium, remember, can't give up a hydrogen, but it can react with hydroxide, making water give up that hydrogen. Now, sodium hydroxide is a strong base, meaning that this is going to revert back into ions. So this cation is neutral, because anytime it produces a strong acid or strong base, it ends up being neutral. Whereas looking at the cyanide ion combined with water. So the cyanide ion is negatively charged. It doesn't have a hydrogen to give up, but it can accept that hydrogen from water, making the hydrocyanic acid and leaving behind hydroxide. Hydrocyanic acid is a weak acid, so it does not have to split apart. We're going to have a lot of that acid overall, and this does produce hydroxide. So this is basic. So this would produce a basic solution overall. Let's look at the next one. Calcium bromide. We split it down the middle. Calcium is going to react with water, and the bromide is going to react with water. I'm not worried about these being balanced overall. So calcium is trying to be acidic. It does not have a hydrogen to give up, but it can accept and react with the hydroxide, to force water to give up that hydrogen. So this will make calcium hydroxide. Remember, this is one of those that is on your strong base list. So this will be neutral or will be no reaction overall because it will revert back into ions. Looking at the bromine, and here's why I say look at both. Don't just assume that if one is neutral, the other one reacts. The bromine is going to accept a hydrogen to make hydrogen bromide or hydrobromic acid, leaving behind the hydroxide. Hydrobromic acid is a strong acid, meaning that it is going to turn back into the ions. So this is also neutral or no reaction. So this overall is a neutral salt. So if only the cation is acidic and the anion is neutral, it is acidic solution. If the cation is neutral and the anion is basic, it is a basic solution. If they are both neutral, it is a neutral solution that you can pick out overall. All right, so we've talked about several different situations. I want us to look at this one together though. Here we have NH4OCl. There are two polyatomics here, so we're going to split it into our cation and anion. Whenever we look at these separately, so our cation ammonium is going to react with water, and our OCl negative is also going to react with water. And same thing, ammonium actually has a hydrogen to give up. So when it gives up a hydrogen, it leaves behind ammonia and produces the hydronium ion. Ammonia is a weak base. So this cation can act as acidic. Looking at our anion, the OCl negative, it does not have a hydrogen to give up, but it's negatively charged, so it can accept a hydrogen. So this can make HOCl, leaving behind hydroxide. HOCl is not on our strong acid list, so it is a weak acid. So this, because it produces hydroxide, can be basic. So how do we know what this solution is when we have an ion that acts as an acid and an ion that acts as a base? In this case, we have to compare the Ka and Kb values for the two. So if Ka of the cation is equal to Kb of the anion, this salt is neutral. If Ka is greater than Kb, the acid wins, so it would be an acidic salt. If Ka is less than Kb, the base is stronger and it will be a basic salt. So we have to know the Ka and Kb values of these two to be able to compare them. Now, pay attention that you need the Ka of the cation and the Kb of the anion. We cannot necessarily compare the Ka and Kb of the weak acid and weak base that it turns into. We need the ions themselves. Is going to make it a little more accurate for us. So I looked these up. In the back of your book, you have a table of Ka values. And it tells you that the Ka of ammonium is 5.6 times 10 to the negative 10th. It does not have OCl negative listed, but it has its conjugate weak acid, which is the HOCl. So we can change this into Kb. Remember, by doing the 1.0 times 10 to the negative 14th divided by the Ka value, the 3.5 times 10 to the negative 8. And that tells us that our Kb value for this is 2.9 times 10 to the negative 7th. So the negative 7th is a smaller exponent. So whenever we compare the Ka to KB wins. So this is a basic salt for us. So if both can react, you're going to look for which one has the stronger Ka or Kb value. All right, there is a shortcut if you're just trying to do something quick to decide what type of problem you need to do. For the shortcut, you can simply look at what is the parent acid and parent base of the cation and anion. So for this ammonium chloride, we can say, okay, well, ammonium is going to be related to ammonia, whereas chlorine is going to be related to hydrochloric acid. Ammonia is a weak base, so that is possible. Hydrochloric is a strong acid, so that would be neutral. So here, since our cation can react, this we would know would be an acidic salt. Now that is just kind of real quick and dirty way to determine would it be acidic or basic. However, pay attention to the question. If it tells you to write out the hydrolysis reaction, or it asks you to justify the answer, you cannot do the shortcut. You have to write out the full reactions that we just did using the ions in solution. So this would only work like on a multiple choice where it wants to know, is it acidic, basic, neutral, that kind of thing. If it's a short answer where it wants to know if it's acidic or basic or neutral, and it wants you to justify your answer, you have to write out those hydrolysis reactions. All right, so let's look at how we combine this with what we learned yesterday with finding like pH, pOH, things like that. So here it wants us to know what is the pH of a 0.1 molar NaOCl solution. Now we have to figure out, what are we looking at? What actually reacts here? What ions are we producing? So here's where to figure out what problem you can do. You can look at the individual ions. So you can do the shortcut to figure out, do we need to focus on the cation or focus on the anion? So sodium, remember, doesn't have a hydrogen to give off, so it would have to react with hydroxide to make a base. OCl would accept that hydrogen. So since sodium hydroxide is a strong base, that would end up being neutral. The HOCl is a weak acid. So this is the ion that we want to focus on. We want to deal with that anion and that hydrolysis reaction. So the hydrolysis reaction for that is the OCl negative reacting in water. And that produces the HOCl. And what's left over is the hydroxide ion. Now, this, remember, is a weak base forming a weak acid. So anytime we have a weak acid or weak base, remember, we have to use an ICE table to find the pH or pOH. So for our ICE table, excuse me, remember, we ignore water. Since it's a 0.1 molar NaOCl, that is going to be our concentration of the OCl negative ion. And we have none of the parent acid or hydroxide to start with. From the previous problem, we found, we found that Kb of OCl negative was 2.9 times 10 to the negative 7. So we need these equilibrium values to plug in for KB. So since we have 0 on our product side, we have to add by a factor of X on our product side, decrease by a factor of X on our reactant side. And those plug into our KB equation. So we have X times X, or you can combine that into X squared, over, here we can ignore our X, so we can just do 0.1. So we can figure out that X, whenever we multiply by 0.1 and then do the square root, X is equal to 1.7 times 10 to the negative 4th molar, which is going to be our hydroxide concentration when you plug that back in. Now, we cannot find pH using hydroxide directly, but we can find pOH by doing the negative log of the 1.7 times 10 to the negative 4th. So we get that pOH is equal to 3.77. Remember, since the concentration has 2 digits, our pOH needs 2 decimal points. And now that we have pOH, we can subtract from 14, to get our pH, which is going to be equal to 10.23, which does pair up with this being a basic salt, with that anion being basic. So you're going to be able to take a salt and actually figure out the pH or pOH, similar to what we did yesterday, dealing with our typical acids and bases. All right, let's look at another problem. Here it wants to know what's the pH of a 0.20 hydroxyl chloride, which it gives you the formula for anything weird. It tells you that the hydroxyl chloride is N2H5Cl. And then it would give you like a Ka or Kb value to go off of. And here it tells us that our Kb value for hydrazine, which is N2H4, is going to be equal to 1.7 times 10 to the negative 6. So yet again, we can kind of figure out, I'm going to rewrite this to the side. We can figure out which part of the equation we deal with, the anion or cation, split it down the middle. So the hydrazine, the N2H5 can give up a hydrogen to become N2H4 negative, and chlorine can accept a hydrogen to become hydrochloric acid. The hydrazine is going to act as a weak base because it's not on our strong base list, while the hydrochloric acid acts as a strong acid. Therefore, that would kind of cancel out and be neutral. So here we're going to deal with that cation. So the cation, that N2H5, which would be plus, would react with water, and that would produce the N2H4. I apologize, that doesn't have a charge. And that would produce the H3O plus whenever it gives up that hydrogen. So here's our overall reaction. For our ICE table, it told us that we had 0.20 molar hydrazinium. We don't have any of our ions originally, so we have to add by X on our product side, subtract on our reactant side. And here's the thing, here we have hydrazinium, not hydrazine, but it gave us the Kb value. So we need to figure out what the Ka value is, because Kb is not going to have hydronium in it, or the H3O plus. So we need to find the Ka value by doing the 1.0 times 10 to the negative 14th divided by the Kb value, the 1.7 times 10 to the negative 6. And we get that our Ka value is equal to 5.9 times 10 to the negative 9th. And that, remember, is equal to our products. So our x times x. And we can ignore x for our reactant. So divide by the 0.20. And we get that x is equal to 3.4 times 10 to the negative 5th molar. And that is our hydronium concentration, or our H plus concentration. So since we have H plus, we can plug straight into pH. And we get that this has a pH of 4.46, which is less than 7, and acidic, which matches up since the cation is the one that would react. So that's how we know if it's acidic or basic, based off of just the cation or anion, because they're all going to work out with their Ka and Kb values. All right, let's look at this one. Here it wants to know, is 0.2 molar ammonium fluoride acidic, basic, or neutral? And it wants us to justify our answer. So remember, anytime it says justify, you must write out reactions. So ammonium fluoride, we're going to split it into the ammonium ion and the fluoride ion. Both react with water. So ammonium has a hydrogen to give up, so it'll give up that hydrogen to produce ammonia, and that hydrogen attaches onto the water to make hydronium. This is a weak base, so this does act as being acidic. Remember, you can't just stop there, you have to do it for both the cation and anion. So for our anion, our fluorine, it's negatively charged. It can accept that hydrogen, make hydrofluoric acid, and leave behind a hydroxide. Hydrofluoric acid is a weak acid. Therefore, this also acts as being basic. So yet again, we have both. We need to figure out, is this acidic or basic? So we need to compare our Ka and Kb values. So we need the Kb for the anion. So remember, do 1.0 times 10 to the negative 14th divided by this Ka. And we get that this has a Kb equal to 1.4 times 10 to the negative 11th. So comparing Ka and Kb, Ka is greater because it is to the negative 10th. So this is going to end up being an acidic solution because the Ka is the higher value. And we're going to go on to the next one because I'm almost out of time. So here, if we want to know what is the pH of hydrocyanic acid, here you can treat this as the same. If we were looking at, this is not a salt, this is a weak acid. So just like we were doing with our salts, we have to use an ice table for this. So hydrocyanic acid itself would react with water. Remember, acids give up their hydrogen, so it would produce the cyanide ion and hydronium ion. So with our ice table, it tells us that this is 0.0030 molar hydrogen cyanide or hydrocyanic acid. We have none of the ions initially. We know we have to increase by a factor of X on our product side, decrease by a factor of X on our reactant side. It would have to give us the Ka value. So Ka for hydrocyanic acid is equal to 6.2 times 10 to the negative 10th. For some reason.